third part of this lecture on the Ax-Schanuel theorem for the J function will be about the differential Galois theory. So differential Galois theory is an algebraic theory of linear differential equation that gives you a group attached to each equation that measure the way you can solve an equation by formula. The way I will present it here is more geometrical, so it is not the full general Galois theory of linear differential equation, but just a particular viewpoint, geometrical viewpoint on it. And I will just give the few statements we will use to prove our main theorem. So let's start with X that will be a smooth algebraic variety over the complex. So I don't want this to be closed or compact, so I can always take out the singular point in X. So this is not a real hypothesis in what we are doing. Algebraic is important. And over the complex number 2. So in NG, inside some GLN-C, maybe it is not this N, will be an algebraic group. An algebraic subgroup of the group of matrices. And so in our example, what we are interested in our case, we will get X will be Cartesian product of y to y n times. And G will be Cartesian product of PSL2 of C times PSL2 of C n times also. So this is the space of our, let's say, independent variable, so there are many of them, and these are the group that will structure our linear differential equation. So Galois theory is something about, or differential Galois theory is something about a linear connection, integrable linear connection. So in our situation, we are interested in functions, so we'll call small u over some open domain in X with value in the group G, which is so holomorphic, on D in X. This something just open, not Zarisk open, just open for the usual topology. And we want to solve some equation. So this U will be a solution of some partial differential equation that I will write this way. Let's say, because our main example is in the Cartesian product, I will call y1 coordinate in the first one, y2 to yn. And in general, I will call y1 to yn coordinate on X. And so we have something looking like that. This is some matrix of y, all the y inside, times u. So we want to solve such system here. We have n equation. And what happened when you look, okay, if n equal 1, so you have just one variable here, you're just looking at linear ordinary differential equation, and you have the Cauchy theorem that ensures that you have local holomorphic solution, and it describes you even the set of all these solutions using initial condition. So here it is more delicate. You have the all systems like this are not compatible. So this is what I wrote here. Just let me add something here. Because we want a solution to live in G here, we need this matrix to be at each point y in the Lie algebra of G, which is a tangent space at the identity. Okay, so meaning that this as matrix of function, we are living here. And here we allow, as I said before, x is not closed, so you can take out some singular point if you need, but you can also take out pole of a rational function if you need, so you can just say that this matrix have coefficients that are rational, and it means regular on a Zariski open subset, which means that up to some restriction, you can assume x is smooth, and these are in fact regular functions on x. And so, to be sure that such a function exists, you need to impose something on the AI that are called Curvature Condition, and you have this theorem which is I don't know who proved that theorem. It says that if you want your equation to have all the solution you need, so you want that for all initial conditions in x cross G, there exists a solution, a solution such that u of y0 is equal to u. Maybe 0 is here. Yeah? So you have an initial, you have a solution going through any initial condition. This is equivalent to this condition that I will write here, dAi over dyj. Yeah? This is a function of all the y minus dAj of dyi is a commutator of ai and aj, which is ai aj minus aj ai. A nicer way to write this is to write this as equality of differential form. Yeah? So the equation now is du so minus au with A, which is now not a matrix of function, but a matrix of form that you obtain this way here. Then you write this equation in this basis, you get this one. And this condition here, this zero curvature condition, is now dA equal A wedge A, where this is product of matrix, but as the coefficient are one form, these are the only way to do a product of matrix of one form. So this is an hypothesis we will put. So we are looking at the system with this hypothesis. Yes, this hypothesis here. Okay, I will have to use at some point a non-linear version of this theorem, which is known as Frobenius theorem. So I will give this theorem here. The proof of this theorem, and then that will imply this one, is just a nice way to use the usual Cauchy theorem. So I will not give the proof here, it involves some analysis to prove Cauchy existence and unicity theorem for solution of ordinary differential equation, non-linear. And then you use this to prove this Frobenius theorem in the holomorphic case. If you are in a smooth case, non-holomorphic, let's say real case, for instance, so you need the nice Cauchy-Lipschitz theorem. Yeah? So the theorem is here. Let X is always a smooth algebraic it can be analytic in this situation, but what you're looking at are one form. One form on X. And sorry, you take only K of them, and you assume the rank of this form is constant equal to K. So they are linearly independent at any point. Okay, then, where is my, here's my theorem. And then you had a new condition that is this one here, but written in this general setting. The condition is this: for all I, d omega I is 0 modulo the form omega. This is known as the Frobenius condition. Then, each time you take a point, I choose y to write a point in x. Okay. Each time you choose a point in x, there exists some subvariety of x which is analytic, immersed, subvariety with y in L, and the tangent of L is the kernel of this form. E equal 1 to k over L. So at any point of L, you have this subspace, the kernel, this subspace, the tangent, and then they coincide. So I will not give the proof here. As I said, it is a consequence of Cauchy theorem. You can find it in many textbooks in differential geometry. So what I want to look at, there are consequences. So first, this theorem implies this one. Yeah, so you have to, the form here are this one. So here, omegas are coefficients. Entries, let's say. Entries is better. Entries of the matrix d big U minus AU, where U are just a canonical coordinate on the canonical function on G associated to this embedding. So here you have n square canonical function that gives you n square canonical function here that are organized in matrix, and so it gives you some form here, n square form. And from this n square form you can extract basis and see that this condition will imply this one. Now there are two lemmas, okay, that are consequence of this theorem here. I can envelope this and put this one inside. So the first condition is that the solution will be described by just one solution and a constant matrix. So let me write the statement here of this easy lemma. Is U is a solution then and C is a constant matrix in G, so it is G. You see that these are non-constant matrix, and now you take really a point in G. Then U times C, okay, meaning that your functions time on the right a constant matrix, which is a new function here, is another solution. So this is not consequence of this is a consequence of this formula. And now you have a more precise statement, that is, if U1 and U2 are two solutions defined on the same disk, two solutions on D, then there exists some C such that U1 is U2 C. Yeah, so it is. So this is just computation. You take this one, you put in the equation proof, and you do the computation. Now here you have to find this one, and so you take a point y in D, and you write this equation at the point. So it will give you the C. The C must be U1 of y times U2 of y minus 1. So you take this C, and from U1, using this C, you build a new solution, and then by Cauchy theorem, or by this Frobenius theorem, it must be C2. And then the last lemma here is that a solution, can be analytically continued along any path. So there is an analytic continuation of any solution. If maybe lemma, any solution can be analytically continued along any path. I will just do a draw before going to the last part. To explain this, so you have your manifold X, you have your open subset D inside, you have your solution living here somewhere, then you take any path from 0, 1 to X with starting inside the disk, and then you try to continue your solution, and you from D to G a solution of your differential system here. Then what happened, that from Frobenius theorem, you know that at any point, any blue point here, you have a disk with a solution. Any initial condition, you have a solution. So you have many solutions here. So using all these disks, any point, you will cover this compact subset with some open ball. Then you can extract finite covering. And then finite covering. And then you have a solution, a white solution here. You have a blue solution here. Using this lemma, you can change the blue solution to coincide with the white one. And then they are holomorphic functions that coincide on an open subset, so your solution is in fact defined in this domain here. And you repeat finitely many times these things, and you arrive to a domain which is union of ball like this. That will give you your analytic continuation. Right? So I have other lemma, but not directly on the solution, but that involve the Zariski closure of the solution, so the smallest algebraic subvariety that contain the graph of a solution. So now let L, which is x cross G, what I will call a leaf, an integral leaf. And what does it mean? If you know the Frobenius theorem, as I told you, that there is this maximal blah blah blah, mean such an analytic submanifold, but you can think it as the union of the graph of all the analytic continuations of the solution U. Union of graphs of all analytic continuation of a solution, of a given solution. Okay, analytic continuation may not be well defined. It can gives you a multi-valued function. So the graph is not just the graph of a solution, but the graph of all these continuations. You can think about the logarithm that is not well defined, but when you do the analytic continuation, it gives you a good analytic curve into C cross C. Maybe not good everywhere, but good on C star cross C. Okay, and what I will denote by Z, so a given solution, I will call it Z of L, or sometimes I will call it Z of U, is the Zariski closure of L. And in an equivalent way, it is a Zariski closure of the graph of U. Okay. Remember, U is something from X to G, no, D to G, so it gives you, the graph is in the product X cross G, and the Zariski closure, this is an algebraic variety, so it makes sense to look at the Zariski closure. And so here also I have few lemma about this Zariski closure that will lead us to the definition of the Galois group. So the first lemma, that this space is irreducible. Okay, it is not very difficult if you take two polynomial functions on this set here, such that the product vanish on this space, then this means that the product vanish on the graph of U. This means that these two polynomials here, when you compose with U, you will get two holomorphic functions on D, whose product is identically zero, so one of the two must be identically zero, meaning that one of your two polynomials must vanish on the graph of U. It is what is called irreducible. second lemma, okay, which has something to do with the action of G on G by the right, that if you take a matrix in G, meaning a constant matrix, then the Zariski closure of the solution or the graph of this solution here, it is a new solution obtained from this one by right multiplication by a constant matrix. As we say, this is a new solution, so it is another leaf corresponding to another solution here. This is just the Zariski closure of L, and right after you apply the multiplication by C on the right. Yeah, so this is an easy consequence of the fact that the multiplication on the right, translation on the right by C, act on this space in a very nice way. It is an algebraic isomorphism. Okay, then from this we get other lemmas. Maybe this lemma is less easy. So you take two solutions. Two solutions defined on the same disk. Then, if at some point the graph of U1, it is U1 here, cut the Zariski closure of the graph of U2, then all the graph of U1 must be inside. So let me say something. If there exists Y0 and U1 of Y0, so it's a point on the graph, inside Z of U2, then all the graph, then Z of U1 equals Z of U2. In particular, all the graph of U1 is inside this. So we have only to prove that the graph is inside, as if the graph is inside, then the Zariski closure of the graph is inside. Yeah? But because of this equality, the fact that one is inside the other, we will prove that you take U1 here, U2 here, and you see that they are the same dimension. So they're included with the same one into the other with the same dimension, and they are irreducible, then they are equal. So we only need to prove, we want to prove this, we only need to prove the inclusion. Okay, and here is the point where we are using the full Frobenius theorem. Yeah, so I will write the proof here. Okay, these are just more or less formal manipulation, but here there's really something to do. So among all the equations, among all the one form that describe your differential equation that we start with, du minus lu equals 0, you can select k of them that are the basis of your equation restricted. Okay. So such that omega 1 restricted to the tangent of z, so I will call z this one, are linearly independent, are independent. So you can do it on a Zariski open subset. Yes, and Then I will look at the set of P in Z such that the dimension of the kernel of the intersection of the kernel of omega I is easy is equal to okay, excuse me, erase this for now, is equal to the dimension of M. Okay, what happened now is that the dimension of the kernel is always dimension of X or smaller or bigger, let's say. So, and it's always a priori bigger, but it's always dimension or smaller because you have graph inside. Yeah? So what you're really looking is this here, and this is a risky close. It is a risky close because this dimension of the kernel bigger means that this one form here, the rank is smaller, and the rank smaller means that some minor, you write your form in one over the other, you have a matrix, and some minor of this matrix is 0. So this is a closed condition here. So it's a risky close, and it contains the graph, the tangent contain the graph of U2. If you take a point in the graph of U2, all the tangent of this graph is inside the tangent of Z, and this form vanish exactly on the tangent of C2. So you have equality in this point here. So it is the risky close, it contains the graph of U2, so it is Z of U2. Yeah. Now you have a point here, and you have this condition there. So through y0, u of y0, you get a leaf by Frobenius. So as I said, this is equal, and in fact equal means bigger than or equal, so you get a leaf by Frobenius theorem. Which dimension of the leaf is the dimension of X? So you get something here whose dimension is dimension of X that kills all this form. But this form, as I said, is linear. But this form, if they vanish, it means that this form here vanished, that they generating all of them, all the entry. Excuse me for the small line here. So among them, you select a basis of form here. You have n square form, you select a basis. Then you look at the kernel, and then the kernel gives you a L, a graph, but inside Z. But this L, also, as it cancels all this form, it will cancel all this form here, and it has a good dimension. So this L is also a solution. L is the graph of U1. So you produce a graph, and you verify that this graph is in fact the graph of U1. So it proved the inclusions, yes? The graph of U1 is inside this Z of U1, so you have, as it is Zariski closure is inside. Then, using this, you have new small lemmas that say that the set of all Zariski closure of these sets will give you a partition of your space. So if L1 and L2 are two leaves, meaning two solutions of your system, then if the intersection is different from 0, the Zariski closure are equal. If the intersection of the Zariski closure is different from 0, then they coincide. So remember here, I just said it very quickly, that up to some restriction of A on X, we can assume here that A is a regular matrix, meaning no poles. AI have coefficient AI are in the real algebra of G with coefficients that are regular function on X. So you can always assume X is affine. You cut out some part to get it in affine space. And then you take out the singular locus, you take out the pole, and you have a new algebraic variety on which everything is regular. Be careful that if you allow pole, then at the poles of AI, this condition may fail. Okay, but here, because of this, it is implicit here, we use this regularity condition. Okay, so this is a consequence of this one. Yeah? If there are someone in the intersection, then you call it y0, u3 of y0, and then you see that z of the leaf going through this point has a Zariski closure that coincides with this one and with this one, so everyone coincides. Then here is the definition we have in mind, the definition of the Galois group. So what is the Galois group of our leaf L? So L is the leaf of the differential system. Start with that. And here is a leaf of du minus au equal to 0 is A. So these are the canonical, is a one form, which is a matrix of regular one form. On X. Okay, if it is a leaf of this linear system, then we define the Galois group of L, which is a stabilizer in G acting by right multiplication of the Zariski closure of the leaf, meaning that here you are selecting the C constant matrix such that if you start from your leaf and you do the right translation by the matrix, the right multiplication by the matrix, then you still get something included in the Zariski closure of L. And in some sense, these are new leaf that you cannot distinguish from this leaf using polynomial. Okay? that satisfy all the same polynomial equation. Okay, and by standard argument from theory of algebraic group, groups. This Galois is an algebraic subgroup. Of G. Yeah, you just write that it's stabilized Zariski closed subvariety, an algebraic subvariety, so you can write it at the level of polynomial and you do elimination and you get that this subset of G is defined by polynomial equation. Here again, I will end with two small lemmas about this Zariski closure and this Galois group. And then we are going to examples. Okay, so the lemma 1, or the lemma, I don't remember how many of lemma I wrote, so no numbers. If you look at it, if you fix L, a leaf, and C, a constant matrix, then the Galois of LC is something like C, the Galois of L, C minus 1. Okay, so this group has a subgroup of G depend on the leaf you are looking at. But if you change the leaf to another one, any other leaf can be written like this, then the group you obtain is just a conjugate, okay, of this one. So as an abstract group, it is well defined. Only the embedding into the group of matrix is not well defined and depend on the choice of L up to conjugation. Okay. Then the second lemma from all the things I wrote, that if you have two solutions, or better than that, if you have 2 points, so y0 is 0, and y, let's say 1, u1, 2 points in x cross g, and in fact 2 points in z of L. Yeah. And you assume that these 2 points are over the same y. Yeah, so they are in the same fiber for the projection of x. Then there exists a unique C, which is in the Galois of L, such that u0 is u1 times C. So the Galois group is stabilizing Z of L, but its action on fiber, you see the Galois group is only acting by right multiplication, so it's acting on this factor here, it will preserve the fiber of this projection on X, and it's acting simply transitively on each fiber of Z. So the fibers Z y0, which is Z cut by this space, are orbits of the Galois group. Here again, Z means Z of L. They are orbits of the Galois group. So, in fact, this is a bundle of orbits. Each point, you have an orbit. But this orbit may change from one point to y0, the 0 is here, excuse me, to another one. Okay, let us look at some example we have in mind, and then I will present you the two tools we will use. Okay, example 0. Example 0 is this: you take x to be c star minus 0, but not as a group, but as a space. Your group G is the additive group, meaning the set of matrices like this. And your differential system is this one: B of 1, U 0, 1 is 0, 0, 0. Okay, the Lie algebra of this one is matrix are all, the entries are all 0 except this one here. And so I have to choose a form here, a one form in one variable. And so I choose this one, dy over y, and then the matrix is here. Using this, you know a solution of this system. You know a solution. It's a du equal. Okay, so the solution is given by u equal to logarithm of x. Yeah. Okay, then you can see that this graph of this solution, it's in here, is invariant by right multiplication by this kind of matrix. Yeah, this is just because log of x is not well defined. Yeah, it has some monodromy. If you do analytic continuation, you will obtain log of x plus 2i pi, which is this one. So this matrix is sending the graph of the solution to the graph of the solution, to another determination of the solution. As it is stabilizing the graph of the solution, it is stabilizing the Zariski closure of this graph. So this means that these belong to the Galois group of the logarithm. Yeah. But if the Galois group is a subgroup of this one that vanish on all multiple of 2i pi, then the Galois group of the logarithm is the additive group. Okay. The example 2, or the example 1, is our equation, the equation we want to study. Yeah. So x is our space y. Remember that y is c minus these 2 points, and g is PSL2 of C that we see as 2 by 2 matrix up to some identification. And then our system, so is a 3 by 3 system given by the entries of this matrix of one form. And here you have 0, dy, our function r of y dy, 0. Here is u. And now you get a nice solution, u. The solution you obtain from J. You have from the J function. You remember all these things from J to T to U. We have three different models for the same differential equation. So each time we have a solution from the differential equation for J, we get a solution here for this one. So there is a graph coming from here. And now, because these identifications are compatible with the group action, each time you have an homography that leaves J invariant, it will be leaving the graph of U invariant. So P SL2 of Z leaves the graph of J invariant. In fact, it leaves J invariant, so its graph. And has the action here is given in the linear model by right multiplication by the same matrix, in fact, the inverse of this matrix, then this group will act on this space here, the product of these two, and will leave the graph of U invariant. It will not leave U invariant. You will go from one determination of U, which is a local, to another one. So here, maybe the solution is not good, but a solution, because you have many determination of the inverse of J that will give you a different function that have all the same graph, all the same leaf. So this leaves the graph of U invariant. Then it will preserve the Zariski closure, then it will be in the Galois. PSL2 of Z is in the Galois group of this local solution you have chosen. Now you take Zariski closure. This is Zariski close. This is included in PSL2 of C, so it must be equal. Yeah. And the third example, which is example 0, so example 2, the product case. Because remember that we don't want to take one solution in J, but we want to evaluate J in different variables, so we want to take as many as J, as different, to evaluate them on a different function. So meaning that we are looking at X, which is Y to the end, and G, which is P SL2C to the end, and remember the tilde notation, yes, U tilde is now a block diagonal matrix with U1, U2, U3. A tilde is block diagonal with this is 0, R of Y1, dy1, 0, and dy1. I will do a bigger block, 0, R of Y1, dy1, 0, dy1. This is the first block, and you do all the block, and the last one, 0, dyn, R of yn, dyn, 0, and you have as many blocks as you want, and then leaves of this big system, which is just a product of the same system. It's a product of the same system written in different variables. And we call these, they are just product of leaves. With this to this that are leaves of the example 1. Now we have a set that is a Cartesian product of some other sets, and it is easy to look at the Zariski closure. Yeah? The Zariski closure of a product of two sets is a product of the two Zariski closure. So because we are really looking at this and not at a subspace of this. So the Zariski closure of this, the Zariski closure of L1, the Zariski closure of Ln. Yeah, it is clearly inside, and then you cut. You fix point here, you cut everything by fibers, and you will get this equality. And because of this, the Galois group of the product is the product of the Galois group. All of them are PSL2, so this is PSL2 of C to the n, which only means that if there are no polynomial relation between the entries of this one and the independent variable, and then you move everyone to other kind of independent variable and other kind of relation, then you will have no relation at all between all of them. Okay, so let me end with the two tools we want to use. So the first tool is the Resolvent Equation. So I will not need exactly all the equation, but just a particular property of this. So it is a resolvent equation in Galois theory is an equation that has an algebraic solution or a rational solution when the Galois group is smaller. So it is an equation attached to a group. You say, let H be a group into G, and you want to know whenever this will be the Galois group of your equation. So start like this, and we take, so as usual, we take our differential system, you take the Galois group, the H subgroup, and you want to have something that characterizes the fact that the Galois group of this, or you take, it's better to take a leaf. So take a solution here, and look at the Galois group of this solution, and the question that, is this a subgroup of H? So the theorem here involves the projection of rho onto the quotient. So rho will be the map from X cross G to X cross G over H, which is just the quotient map. Okay, so this row is a quotient map. And the theorem we have is this, that the Galois group of the leaves is inside H if and only if the image of L is a graph of a rational section. A rational section from x to the quotient here. And so there will be a differential equation for that differential equation. I will show you an example here, but we are not using the differential equation, just this property. And this property is not so difficult to see that if rho of L is a rational section, then you take rho minus 1 for L, it is Zariski closed. It is stabilized by H, and it contains L. Okay, so the Galois group of L is inside H. And now, if you look at this sense, then you will look at rho of Z of L. This will be outside some codimension 1 plus, this will be an algebraic manifold. Algebraic subvariety. But if you look at the fibers here, the fibers of this over some point y in x, then I said these are H orbit of H. So the rho of Z of y is a point. Yeah, so you have an algebraic thing in the product, so the algebraic subvariety of the product, such that above each point x in x, you have just one point in your variety. So it is the definition of a graph, or one definition of a graph of a rational map. This is the first tool. The second tool is the tool we already used, or we already showed, which is the fundamental form. I call it principal, excuse me. The principal form, which was this omega, u minus 1 du minus u minus 1 a u. And then what happened, that is pretty good, is that this form is, as I said, very compatible with the right action, the action by right multiplication. And so the theorem we have here is that if you take omega and you restrict this omega to the manifold rho minus 1 rho of L, yeah, so you take rho like this, you leave, you put this leaf here, you come back. Then it takes values in the Lie algebra of H. Okay, so you have the same H, same things here. You do the same construction, and you have this theorem, which is maybe it's theorem from Élie Cartan. And so the proof is quite easy, and we will end with a proof. So you choose a solution. Choose U from D to G as solution with graph inside L. And then you do what is calling what we call the gauge transformation, and the gauge transformation is just a map from local gauge transformation, d squared g to d cross g, that's an y and your solution and a point u. Let's say this is big U, into y and u minus 1 of x of y times your big U. So you see, I'm relating the solution by the left, not the right. Then if you pull back, so maybe it's p minus 1, okay, your form is here, you want to push your form there, so you use p minus 1 to pull back your form omega, then it is only u minus 1 d. So in some sense, you use a solution to convert this space here, or this space, to you map the graph of u to the identity. What happened that this gives a kind of rectification of your form. So this is just computation, okay? You put this formula in the formula from omega. You write that this is a graph of a solution, that this satisfy d of the graph is minus a, is a times the graph, the function, and so you get this. It's just computation. But now, everything is done here, yeah? Because when you do that, you have that your subspace rho minus 1 rho of L is now sent on d cross H, yeah? As your section U is sent to the identity, okay, has left multiplication commutes with right multiplication, it will send right orbit to right orbit, and right orbit of U to right orbit of the identity. The right orbit under H of the identity is just H. So you have this sent to this one. And so this form sends H to its Lie algebra. Yeah, as it is more a Cartan 1 form. Okay? It is more a Cartan form. On a Lie group. On a Lie group, this form takes always value in this Lie algebra. So up to a change of coordinate, the form takes value in the Lie algebra of H. But the value taken here do not depend on the coordinate you choose to write your form, because the value are the same. Change of coordinate are changed by precomposition. So this is the proof here, and we will use this theorem here, and also this theorem here in the next lecture, lecture 4, where we will prove the main theorem, and then in lecture 5 apply it to the J function.